Bond theory. This theory explains how atomic orbitals come close to each other and forms bond. So as the title of the theory suggests, valence bond theory, the first point is the valence orbital having unpaired electron orbitals having unpaired electron of two same or different atoms overlaps to form covalent bond. By sharing their valence electron. Example: hydrogen with one electron and hydrogen with another electron, but opposite spin of the electron can come close to each other and can overlap to form H2 molecule. After the overlapping, the individual identity of the atomic orbitals are lost. Okay. Second is after overlapping of atomic orbitals, the individual property of the orbitals are lost. Third, the covalent bond formed are parallel to the region of the nuclear axis of the atoms. Example: if this is carbon and this is carbon, if it is forming ethene, then see these covalent bonds are parallel to the axis of parallel to the nuclear axis. Means this is the nuclear axis. So they are parallel. This is parallel to this. This should be parallel to this. This should parallel to this. Fourth, head on overlapping results to sigma bond formation. This is sigma, small sigma. This is the sign for small sigma. And fifth and lateral overlapping results to pi bond formation. It is like this. If one S will come head on with another S, it will form sigma bond. It is a strong covalent bond. If one S will come with one P, it will be overlapping, in which hidden overlapping is taking place. So it is also sigma bond. If two P orbitals will come like this, then also it is sigma bond. But if two Py orbital, if two Py orbitals are lateral to each other, then they will not be able to overlap on a head-on basis. So they will undergo lateral overlapping. They will undergo lateral overlapping. As a result, pi bond will be formed. The first formed bond is always a strong sigma bond. Sigma bond, sigma bond, sigma bond, sigma bond. Pi bond is formed only when there is a double covalent bond or triple covalent bond. The sigma, pi, sigma and sigma. So this was about valence bond theory, and the concept of hybridization which we have studied is also a part of valence bond theory only. According to valence bond theory, atomic orbitals may intermix atomic orbitals valence alone may intermix to form hybrid orbitals so that more covalent bonds can be formed. We have seen in our previous discussion that S and 1P, 1S and 1P, they hybridize to form sp hybrid orbital. And the kind of shape it produces is linear. Similarly, 1s and 2p, they form sp2 hybrid orbital. So these small lobes which are making are actually minima. Here probability of finding electron is maximum and here probability of finding electron is minimum. Okay. So it is sp3 hybrid orbital. It forms triangular planar structure. If one is and all the three P's, Px, Py and Pz, they combine, so they form sp3d hybrid orbital. This is sp2, sp3 hybrid orbital. Orbitals. It gives tetrahedral shape. If one is 3p and 1d, they combine, they form sp3d hybrid. It gives trigonal bipyramidal shape. Trigonal bipyramidal shape. If one is 3p and 2d combined or intermix, they form sp3d2 hybridization and their structure is octahedral. This will be in one plane, this will be above the plane, this will be below the plane. Hence, valence bond theory also gives direction of the bond. The covalent bond formed are directional in nature. The covalent bond formed are directional in nature. Because these bonds can tell us that whether the lobes will be in a plane or it will be above the plane, it will be below the plane, what is its shape, what is its structure, that we can find out from this. And hence, these covalent bonds are directional in nature. This is done. But there are a few drawbacks of valence bond theory also. The drawbacks are, it could not quantify the thermal and kinetic stability of the molecules. Quantify means it could not give any data or value. Okay? It could just say whether the molecule will be stable or not. But how much stable it will be, so there was no numerical value for that. Okay. So limitations of valence bond theory, VBT. First, it could not quantify. Quantify means give value. Give numerical value. of thermal and kinetic stability of molecules. Example, with this we could say that PCl5, it is thermally less stable than PCl3. It is thermally unstable. It is thermally unstable. So when it is heated, it forms PCl3 and Cl2 because this lone pair of electrons, they repel the bond pair. This explanation was not given by gravity, it was given by valence and electron pair repulsion theory. Moreover, even if we compare the lone pair and bond pair of electrons in VVT, it could not give how much thermal instability is there. So this was not quantified. This was one drawback. Another drawback was the assumption that only the valence electron takes part. It could not explain use of core electrons in bond formation. If only valence electron will take part in bond formation, then what will the electrons in the core will do? Are they for no work? It is not like that. Later on it was found that even the core electrons, they take part in bond formation. So this theory was having a limitation. It could not explain the contribution of core electrons in bond formation. It gave no idea about the color of various molecules. It could not give any idea about color of any compound. Colored compounds are generally coordination compounds or decoupling compounds. This again we will be studying little later in detail. As of now, this much is enough. Fourth, it could not explain strength of electron pair donors. Example, say if pH 3 is there, it will have a lone pair of electrons and nitrogen also belongs to the same group. So it will also have one lone pair of electron. Now this lone pair of electron can be donated to any electron deficient chemical species. Which one of this will be doing it with more affinity? It was not explained. This was not explained. That which electron pair donor will be strong. It was not explained by valence bond theory. Now, Fifth point. If you see valency of carbon 6, 1s2, 2s2, 2p, 2. So these two electrons are stable. These two electrons are stable because it is paired, and this p orbital has two unpaired electrons. So carbon could have taken only two electrons. Carbon could have taken only two electrons and it could have become stable by pairing it. But why does it have tetravalency? Tetravalency of carbon was not completely explained. Sixth point. See, there are some molecules which are diamagnetic, there are some molecules which are paramagnetic. Okay, so these are the magnetic properties. If any molecule will have any unpaired electron, it will be paramagnetic, and if the molecule will have all the electrons paired up, it will be diamagnetic. If you will see O2 molecule, according to valence bond theory, all the electrons are paired up, so it should be diamagnetic. According to valence bond theory, it should be diamagnetic, but actually it is paramagnetic. So paramagnetic property of oxygen was not explained or was not possible to be explained. Was not possible to be explained by valence bond theory, and hence again some suggestions were given, and those suggestions are considered to be a theory called as valence shell electron pair repulsion theory. So with that we can find out the relative stability of the bonds, okay, but cannot be quantified numerically again. So that also has some drawbacks. After Vesper theory, a theory was given which is related to molecular orbital theory. In molecular orbital theory, paramagnetic property of O2 is very well explained. Then color of the compound can be very well explained. Okay. Then use of core electrons. You will see that the core electrons also take part in bond formation. Okay. So they can either favor bond formation or they can go against bond formation. Alright. So there are bonding orbitals, non-bonding orbitals that we will be seeing in our next discussions. So our next discussion will be based on valence shell electron pair repulsion theory, and after that we will go to molecular orbital theory. Okay. And I will try to show you some ball and stick model to make you understand how bond formation take place. Thank you.